So from last time, we saw that there's no way you can define a nice enough measure on all subsets of R, so you have to sacrifice on where you can define the measure. So this leads us to this definition of a sigma algebra. So the idea is sigma algebra is where the measure is going to be defined, and only sets in the sigma algebra can be measured. So anything other than the sets in sigma algebra will not be measured. So let's give the definition first. So here's the definition. So first of all, let's let X to be some set. So here it can be really any set. It can be the real line if you're talking about Lebesgue measure, and it can be anything else like contour set, can take your favorite set, or rationals, anything you like. And let's call it algebra. So an algebra, we're going to get to the sigma next. So an algebra is, let's use this curly A. So it's a collection of subsets of X. So by that, I really mean this curly A is just a subset of the power set of not R, but X. All right, so it needs to satisfy the following three conditions. So first condition, I will require that the empty set is in A. So A contains at least one element. Second, I would like to have X take away A to be contained in A for all A in A. In other words, if you have an element that's in this algebra, then its complement has to be inside this algebra as well. So this is closed, sometimes we call it closed undertaking complements. And lastly, I would like to have the following property. So if I have A1 up to AN in A, if you have a finite collection of sets in A, then I would like to have their union. So here I going from 1 to n of AI. That's also in A. So I would like to have their finite union is also in A. So this is our definition of an algebra. So a sigma algebra is slightly stronger than an algebra. So we call a sigma algebra if it satisfies the strengthened version of 3, let's call it 3 prime. So if I take A1 up to AN, and then if I can just keep going, so in other words, I'm having a sequence of subsets in A, then when I take the union of this infinite sequence, when n going from 1 to infinity of these AN, then I require is also inside the set A. So if this strengthened version of 3 happens, we call it a sigma algebra. So here the sigma is really saying the countable union part. So sigma corresponds to this countable union. So without sigma, you only require finite union, but sigma algebra, you require the countable union. All right, so let's take a few examples. So first of all, there's always a smallest sigma algebra, really. So if you let any X be any set, and if you just take the empty set in there, and by the sigma algebra has to be closed under complement, the entire set X being the complement of the empty set has to be in there. And if you just take two of them, then this is an algebra, or it's also a sigma algebra. So sigma algebra. And as you can notice, a sigma algebra is always an algebra. So here is just a note. If A is a sigma algebra, then it's also an algebra. Well, why is that? Well, for the algebra, the only algebra and sigma algebra, the only difference is this finite union versus the countable union. So if you want to have a finite union instead of countable union, well, what you can do is that your union n going from 1 to, not to infinity, of I going from 1 to n of this ai, what you can do is you can say, well, this is a1 union up to an, and then I can make it a countable union by add a bunch of empty set at the end, and that becomes a countable union. So apparently sigma algebra is also an algebra. All right, anyways, so we have a smallest sigma algebra just containing two subsets, empty set and an entire set. It's not going to be a very interesting one because we're basically saying the only thing we can measure are these two sets. Nothing else is measurable. The second example I like to take is the power set of x. Okay, so this is clearly a sigma algebra as well. Well, why is that? Well, it contains every set, so it's certainly close under all these operations. You take complement, you take union, any way you like, you still get something that's still a subset of x. So this is certainly another sigma algebra. So this is also not so interesting. Well, first of all, this is the largest sigma algebra you can get, of course, because it contains everything you can have. It's not so interesting because as we already seen in the case of the real line, there's no way to define a nice enough measure on the power set of the real line. So this set is often really large and is not so interesting to study because there's not many good measures on the set. You cannot define any function on this set. And now I want to give a little bit another example that's not these two. So, well, if you take n for 50, you can say, well, let's take the Lebesgue measurable sets. Okay, that's a sigma algebra. That's not the trivial one. It's not the power set. Let's take something that's different from them. Okay, so let's let the following. So let's x be an uncountable set. So it's not countable. For example, you can take x to be a real line or the Cantor set or any uncountable set you like. And let's do the following. So let's define a set A. Okay. So let's let A to be the following subset of x. So it contains all the set E subset of x. What this E is the following. So either E is countable, or the complement of E, so I use this notation, x takes away E, if that's countable. So I define a collection of sets to be the following. So it contains all the countable subsets of x, and it contains all the sets where its complement is countable. Sometimes we call this the co-countable sets. But anyway, so let's let A to be this collection of sets. My claim is that A is a sigma algebra. So why is that? Well, if I want to verify something is a sigma algebra, let's just verify it satisfies the three properties from its definition. So first, is the empty set in A? Well, of course, because the empty set is countable, it contains nothing. So because empty set is certainly countable. Second is a closed undertaking complement. So let's let E to be in A. Let's just take any element of A, which is a subset of X. Well, elements are in A have either countable or co-countable, so let's break into two cases. So case 1, if E itself is countable, well, in this case, is complement also in A? Well, let's think about it. Well, its complement is certainly not countable because X is uncountable. You're taking a complement of a countable set. It should be uncountable. But X takes away E, even though that's uncountable, is complement. So let's take its complement. Well, you take the complement of the complement, it should give you the E back. So this is countable. So by definition, this X takes away E or the E complement, that's a co-countable set because it has countable complement. So in other words, X takes away E, that should be in A because its complement is countable. And you can write similarly in the second case if X takes away E is countable. Well, what you can do is that, well, because this complement is already countable, then, well, A contains all the countable set, so X takes away E is in A for sure. So in either case, you know the complement of E is in A, so this A is close undertaking complements. And lastly, I want to show to satisfy the third property, which is close undertaking countable union. So let's let En, let's say n going from 1 to infinity, that's a sequence of elements in A. So they are all subsets. And we want to consider their union of this En when n going from 1 to infinity. Well, in one case, because this is a countable collection of sets and each one of them is either countable or co-countable, if all of these En are countable, so case 1, if all the En are countable, well, then what can happen? Well, we're taking a countable union of a countable sets, so its countable union should be countable. There's some standard facts from set theory, so we know this is also countable. Because it's countable, it's in the A. That's just because A contains all the countable sets. And the second case, what happens if one of these E is not countable? So there exists some E, let's say E of big N, that's not countable, so that its complement has to be countable. So X takes away En. That's countable. So what happens? Well, if one of them is uncountable and you're taking a union of them, then of course the union won't be countable. So let's think about what's the complement of this union. So let's take X, take away these En. So what's the complement of the union? Well, set theory tells you this is the intersection of their complements. So the complement is the intersection of all the complements. And in particular, you know this intersection has to be contained in this complement of E big N. Because it's one of them, you're taking the intersection, it can only get smaller. Well, now the X take away En or En complement, we know that's countable. So the intersection of these countable is contained in a countable set. So this one is also countable. So in other words, the countable of this union, the complement of this union is countable. So that will imply it's co-countable, so it's also in A. In either case, we've shown that the infinite union of these En is again an element of A. So this proves that A is closed under infinite or countable union. So that we can conclude A is a sigma algebra. And you can see that this A is not equals to the trivial one. So it certainly contains the trivial one, but it's certainly not equals to A. And you can convince yourself this is also not equals to the power set of x because, well, when x is uncountable, you can always break it up into two uncountable sets. Each one is the complement of the other. So that uncountable set is certainly not co-countable, so it's not in A. So power set of x contains strictly larger number of sets. So here we have a non-trivial example of a sigma algebra that's not the smallest and nor the largest. This sigma algebra is really interesting. You will see this in your assignment. So in the next lecture, we are going to go through more properties of the sigma algebra.